Every single time you send an email or buy something online or even just log in to one of your accounts, you're placing your trust in a secret, a digital secret. It's all protected by these layers of super complex math that we've always just assumed are, well, unbreakable. But what if they're not? What if the very foundation of all our digital security is about to get completely shattered? Let's dive into how our world is on the brink of a massive security revolution. To get our heads around this, let's start with a really simple analogy. Imagine you and a friend, we'll call you Alice and Bob, want to agree on a secret color, but you're in a room full of people. So here's what you do. You both start with the same public color, let's say yellow. Then you each secretly add your own private color. Maybe Alice adds a little red and Bob adds some blue. You then swap your new mixed colors right there in the open. Alice gets Bob's greenish mix, Bob gets her orangish one. Now here's the magic trick. You each add your original private color one more time. And boom, you both end up with the exact same, unique, secret shade of brown. Anyone watching would have a really hard time figuring out how you did that. This simple, clever idea, it's pretty much how we share secrets online right now.
So that little paint mixing trick is the perfect way to visualize a really revolutionary idea that is, no exaggeration, the bedrock of our digital security. It's called public key cryptography. Let's pull back the curtain and see exactly how it works.
Okay, so in this system, everybody gets two keys. The first one is your public key. You can share this with anyone, post it on the internet, shout it from the rooftops, it doesn't matter. Think of it like an open padlock. Anyone can take that padlock and use it to snap a box shut. But, and this is the important part, only you have the second key, your private key. It's the only key in the entire world that can open that specific padlock.
So what's the magic that makes this all possible? Well, it's something called a trapdoor function. The best way to think about it is like a one-way street in mathematics. It's super easy to go in one direction, but it's practically impossible to turn around and go back the way you came. Unless, of course, you have a secret piece of information. That's the trapdoor, and that's your private key.
So what are these mathematical trapdoors really? Well, they're built on what cryptographers call hard problems. And they're called that for a reason. These are challenges that are so incredibly difficult for our current computers to solve that they basically form the walls of our entire digital fortress.
And this right here is a perfect picture of one of those problems. Look at that top arrow. It's really easy for a computer to calculate, say, 5 to the power of some number, and then do a little modulo math. It can spit out the answer instantly. But now look at the bottom arrow. What if I just give you the answer, 12, and ask you to find the starting number? Whoa, that is ridiculously hard. A computer would literally have to guess every single possibility. That's our one-way street, our mathematical trapdoor. So, believe it or not, our entire digital fortress is basically built on just two of these hard problems. The first is called integer factorization. It's the engine behind the famous RSA algorithm. Multiplying two gigantic prime numbers together, a piece of cake for a computer. But trying to take that huge result and figure out the original two primes you started with, a normal computer would take billions of years to do that. The second is the one we just looked at, the discrete logarithm problem. That's the math that powers that paint mixing trick we talked about.
For decades, these hard problems have been our shield, our unbreakable wall. But there's a new type of computer coming, one that doesn't just play by different rules, it's playing a whole different game. And it poses a massive existential threat to our entire security system.
And this right here is the heart of the problem. You see, the very thing that makes these problems hard for our computers is a total cakewalk for a quantum computer. It turns out that the bizarre, amazing way these machines work makes them naturally incredibly good at solving the exact kind of math problems we use to keep our data safe. I mean, just look at the difference here. A task that would take the most powerful supercomputer we have today, longer than the age of the universe, could potentially be solved by a quantum computer in maybe a few hours, or even minutes. Our mathematical walls wouldn't just be breached, they'd just evaporate. So, if we can't trust the difficulty of math anymore, what's left? Where do we go from here? Well, the answer is to change the foundation of our security entirely. We're moving from the abstract world of math to the real, fundamental laws of the physical universe itself. This brings us to something called quantum key distribution, or QKD for short. Instead of building our security on problems that are just hard to solve, QKD builds security on things that are physically impossible to do. It's a totally different way of thinking, and frankly, it's beautiful.
two fundamental rules of quantum mechanics make this whole thing work. First, there's the observer effect. In the quantum world, the very act of looking at something changes it. You literally can't measure a tiny particle without disturbing it. Second, there's the no cloning theorem, which says it's physically impossible to make a perfect copy of an unknown quantum state. These aren't just engineering hurdles, they are hard-coded rules of reality. So how does this actually work? Let's walk through the most famous QKD plan, called BB84. Alice sends a stream of single photons, individual particles of light, over to Bob. For each photon, she randomly encodes a 0 or a 1 using one of two different filters. Think of them like two different kinds of polarized sunglasses. Now Bob, on his end, has no idea which sunglasses Alice used for which photon, so he also randomly picks a pair to measure each one as it comes in. Afterwards, they just hop on a regular phone line and tell each other which type of sunglasses they used for each photon, but not what they saw. Here's the cool part. Anytime they happen to use the same sunglasses, they know they got the same result, so they keep those bits and throw out the rest. What they're left with is a shared, secret key known only to them.
Now, that all sounds pretty slick, right? But what about an eavesdropper? Let's call her Eve. What happens if she tries to intercept those photons mid-flight?
This is where the laws of physics become the ultimate security guard. For Eve to read the photon, she has to measure it. But just like Bob, she doesn't know which sunglasses Alice used, so she has to guess. Now, if she gets lucky and guesses right, she reads the photon and passes it along without leaving a trace. But she's going to guess wrong about half the time. And when she does, the observer effect kicks in. Her measurement actually changes the photon before it gets to Bob. And that change is everything because it introduces errors into what Bob sees. So here's the brilliant final step. After Alice and Bob think they have their key, they take a small random chunk of it and just compare it over the public phone line. If no one was listening, their bits should match up perfectly. But if Eve was on the line, her clumsy measurements will have created a bunch of errors that they can now see. If the error rate is higher than it should be, they know someone was listening. They just throw the whole key away and start over. Eve literally cannot listen without getting caught. It's a perfect tripwire. Now, I know what you're thinking. This sounds like something out of a science fiction movie, but it's not. This is happening right now in the real world. Let's take a quick look at where this unbreakable key is actually being used. Over in Japan, the Tokyo QKD network has actually been up and running for more than a decade now, connecting different high-tech organizations with fiber optic cables that are secured by these very laws of quantum physics. China has taken this to a completely different level. They built the Beijing-Shanghai backbone, which is this massive 2,000-kilometer-long quantum network used to protect super-sensitive data for things like banking and major businesses. And it's not just staying on the ground either. The Chinese Mikias satellite proved that this can even work from space. It successfully beamed down quantum keys to ground stations that were over 1,000 kilometers apart. This is really the first big step towards a truly global quantum-secure internet. So what we're really witnessing here is the beginning of a totally new era in security. We're moving away from a system based on the assumed difficulty of math problems to a new one based on the proven certainty of physical laws. This is the kind of security we're going to need for the coming quantum age. But, and this is a really big but, there is a fascinating catch. To make sure that Alice is really talking to Bob and not to Eve pretending to be Bob, they need an authenticated channel. And that authentication, well, it requires a pre-shared secret to begin with. So, wait a minute. If you already need a secret to start the whole process, then what's the point of using QKD to create a new one? It's a genuine puzzle that engineers are still trying to solve in this never-ending quest for perfect security.